Welcome to Scanner School. This is session number 126. We're talking about antenna polarization. And before we start this week's podcast, I want to thank the supporters of Scanner School. So whether you're going to scannerschool.com/support and you're supporting us at a one-time donation by going to PayPal, maybe you're using our Amazon links before you make a purchase on Amazon. If you're looking for new hardware, you're using our Scanner Master links, or even if you're using Butel software, before you make that purchase, you go and use our Butel links and our brand new eBay links if you're looking for used equipment. Your support helps keep the podcast going. I also want to thank those who help support us on Patreon. Now, Patreon is a month-over-month type of sponsorship platform. And there's three different tiers. The first tier for $1 a month, you're just helping to support us. And really, at the Patreon takes theirs, we're only getting pennies on a dollar, to be honest with you. At $3 a month, you're going to get the podcast delivered to you early. You get your own private podcast feed that you can actually get the podcast as soon as it's available. At the $5 level, you not only get the $3 level, but you also get squelchy stickers mailed directly to your home. Because at $5 a month, it really equates to being about $1 a week or $1 per podcast is really what you're giving us. So again, I want to thank my Patreon supporters who are Greg Harper, Dan, Glenn Blum, Glenn Bryan, Guy Lee, Irvin Thibodeau, James Felling, Jeff Block, Jenny Taylor, John Goldenberg, Ken Newberry, Kenneth Feller, Mark Beebe, Raymond Hill, Richard Armstrong, Ronnie Bach, Sal Marandola, Scott Vorder, Signals Everywhere, Todd Glendy, and William Arcand. Let's start the podcast.
Welcome to The Scanner School, a podcast dedicated to the scanner radio hobby. Class is about to begin. Here is your host, Phil Lichtenberger.
Okay, welcome to Scanner School. My name is Phil Lichtenberger. My radio call sign is W2LIE, and this podcast is here to teach you everything that you need to know about the scanner radio hobby. All the session notes we talk about today can be found on our website at scannerschool.com/session 126. So today we're talking about antenna polarization. And why are we talking about antenna polarization? Because it takes two to tango? Well, I don't know about that. But it does require you to be within the same polarity as what it is you're trying to receive in order to receive it the best. So it's very important when we talk about our antenna setup to understand why things are designed the way they are. For example, why in our vehicle we have an antenna that goes up and down. Why on our homes we have antennas that go up and down, but yet some people have antennas that go side to side. Even worse, why do some people have antennas that corkscrew? All right, well, we're going to figure all that out in just 1 second. And we're going to break it down into two parts here. First, we're going to talk to you a little bit about the theory. Then we're going to talk to you about the practical side. So let's get right into it. So the first point here is that your transmitter and receiver need to, for most of the time, be in the same polarization or in order to have good reception and communication with each other. So a vertical polarized antenna receives a vertically polarized transmission the best. And if you guess that a horizontal polarized signals won't be picked up that well by a vertically polarized antenna, you already kind of understand what's going on here. Right? Since those two are polarized in two different planes, they're not in the same phase. And while it's not really impossible for one to pick up the other, it's going to be extremely attenuated. So before we jump into it, let's just draw a picture, mental picture of radio waves and what they look like here. So again, radio waves typically, right, oscillating sine waves. They go up and down over a set period of time. The number of times that this wave and this cycle happens is called a hertz, right? And we see this on our radio dials as Hz. In the scanner radio world, we talk about megahertz. You talk about in SWL, kilohertz. You start really getting into extreme stuff, gigahertz, right? This is the number of times per second that you have a complete oscillation from zero all the way up, all the way down, and back to zero again. Okay. Now, these waves we can see, right? If we think about a guitar string vibrating, we can see the waveform on the guitar string vibrating back and forth. And we can also hear the sound that that string makes, the audible frequency, we can hear that with our ears. Okay, so now you have kind of a mental picture. It's a sound wave, right? It's a sine wave, S-I-N-E wave. So you have two parts, though, to any radio wave. You've got the electrical field, and then you have a magnetic field. And these are mutually perpendicular from one another. So again, as you have the electrical field, that's your polarization, and you have your magnetic field. For example, a vertically polarized RF signal will have a vertical electrical field and a horizontal magnetic field. So you can kind of see how this is playing out here, okay? Okay, let's talk about linear polarization. Now, the most common type of linear polarization, when we talk about it in the scanner radio hobby, because we're talking more about two-way radios in the VHF and UHF spectrum, it's going to be vertically polarized. Vertically polarized, up and down. This is the most common form, and our antennas are mounted vertically, up and down, right? That's where the name comes from. Vertically polarized antennas can be directional. They can be omni. But the trick here is that the antennas are perpendicular to the Earth's horizon. Now, in a horizontal plane, the antenna is laid down on its side, and it's parallel to the horizon. The electrical signals formed by these antennas move side to side, or parallel to the Earth's horizon. And the magnetic field is vertically or perpendicular to the Earth's horizon. Now, you can also have what they call slant polarization, where the polarization is at an angle, and you can see a mix kind of horizontal and vertical polarized, which is also called cross pole. So why do we have a cross polarized RF signal? So that both horizontal and vertical antennas can communicate with the cross pole signal, right? It kind of gives you that ability to kind of play with both types of polarization. And we're going to talk to that in a minute, and you have an example of this pretty much in your pocket or in your hand all day long. It's pretty amazing. We'll talk about this in 1 second. And this is really something that is cool with me because this is my 9-to-5 job here. So anyway, before we even get there, horizontal and vertically polarized and even slant, that's great. You have a fixed location. You have a fixed antenna, right? You have control over the way that the antenna is mounted. You can guide that waveform vertically or polarized. But what happens if your antenna is in free space, like a satellite tumbling through orbit? Well, I guess tumbling is a bad word to say, but right, the satellite can rotate and can change its position while it's in geosynchronous or going through the sky. How would you communicate with that satellite if the polarization on the antenna is always changing? Well, this is where we have circular polarization. And circular polarization is a great way of communicating with satellites and for satellites to communicate with Earth-based stations because the signal corkscrews through the air, or the signal corkscrews. Okay. And now you can have two different forms of polarization when it comes to circular. You have right-hand circular polarized signal and left-hand circular polarized signal, where one just goes clockwise and one just goes counterclockwise. So if I lost you when it came to circular polarization, imagine what happens if we throw not only circular but linear into the exact same polarized signal. Well, then you get elliptical, and we're not even going to talk about that, right? Because we're just going a little bit bonkers at that point. So just to summarize what we've gotten so far, we have horizontally polarized signal. We've got vertically polarized signal, again, which is the most common for what we're talking about here. We've got slant polarized, which in your pocket is the most common polarized signal you've got here. And then you've got a circular polarized signal, which, again, is all around us, and we use that pretty much every day as well. So on the other side of this break, let's talk about these polarized signals and how things are practically in our hand when it comes to this. This session of Scanner School is sponsored by East Coast Pagers. Now, East Coast Pagers is one of my online companies, and we are a Unication, Apollo, and Swiss phone dealers serving the North American market. Now, if you're looking for a personal use pager or one for your department, we can get you a quote at the very best prices. So why does a company like East Coast Pagers support Scanner School? I think that every scanner radio user should at least put one pager in their collection of radios. The reason why is very simple. It frees up your scanner to just do scanning, and then you have one radio that's dedicated to your local fire activity. Now with a pager, you can have voice storage. You can do tone outs. You can keep it silent. You can go back the next day and listen to what you've missed overnight. It's more than you can do with an out-of-the-box scanner. And with today's pagers having multiple frequencies and even having multiple channels in a scan list, like the Unication G1 can do 8 channels in a scan list. It has 64 memory channels, and out of the box, it comes with 11 minutes of stored voice and a desktop charger. The G2s to G5s, they do P25 phase 1 and phase 2 in simulcast environments with stored voice, paging on conventional and P25. Oh, and they're upgradable too to DMR Type 1 and Type 2. They are more rugged than today's consumer-based scanners. And with a pager like a Swiss Phone S Quad, you won't even realize you're wearing one. It'll help keep you informed as to what's going on in your neighborhood. So again, eastcoastpagers.com or contact me directly, phil@eastcoastpagers.com. Do you have a new scanner? You're having problems understanding how it works? Maybe you're new to the entire Home Patrol database of programming and you can't figure out Sentinel. Did you get a new SDR and you're trying to figure out how to install it? Or you want to learn how to use Unitrunker, DSD+, maybe set up a PieAware, or even just make some changes and you don't understand how the system and the equipment works? The podcast might be great for you, but maybe you need a little bit more of one-on-one help with setting something up. I'm available to do just that with you with our private tutoring sessions. You can book me online by going to scannerschool.com/consulting for a 1-hour session. And it's great because we can actually share computer screens remotely and I can guide you through step by step as if I was sitting right next to you. So again, book me for an hour at scannerschool.com/consulting for your scanner radio one-on-one tutoring session. National Communications Magazine is your personal library of scanner, CB, GMRS, FRS, MURS, and two-way radio articles written by the best minds in the business over the past 3 decades. Your NatCom personal online access account allows you to download the newest issues of America's Hobby Radio magazine, as well as back issues too. So visit natcommag.com to download your free sample issues and sign up today. That's natcommag.com for National Communications Magazine. Okay, so now that we have a bit of a theory and understanding of the polarized signals and the polarized planes and what we're doing here with the antennas, let's get into some real life examples here, okay? So vertically polarized, this is the most common one that we use, right? We have it on our scanners. It's the most common form of polarized signal in the VHF and UHF spectrum. Well, why is that? Think about your car, right? Your FM radio antenna, at least on cars up until they started putting them in other places, the antennas were right there in the fender, right? It moved up and down. When it comes to two-way radios, right, you mount the mag mount or you put the through the body antenna vertically on your car. And again, the way that the antennas work too is it uses the sheet metal in your car to act as the mirror of the antenna so that you only have half the antenna sticking up realistically. But vertically polarized is the best way for things to be mounted on vehicles, on top of radios, on top of towers, on top of buildings, etc., etc. So this is why we kind of have vertically polarized antennas when it comes to the two-way radio spectrum. Now, again, what else is vertical? Like I said, we talked about it on our car. We've got broadcast stations, the FM stations, and even medium wave radio stations are all vertical antennas. Now, vertical antennas have a low angle of radiation, so it means that they can transmit at an angle closest to the Earth's surface. Vertical antennas can be directional, they can be omnidirectional, right? They radiate outwards along the plane of their surface. So typically, if you're looking at the top of the antenna, the pinpoint, the very top of the antenna, that's where you'd have pretty much no RF coming out of it. And it balloons outward along the plane of the antenna. So if you picture a donut, in the middle of that donut would be where your vertical antenna would be. And that's how the RF signal would look in an omnidirectional antenna. Again, omnidirectional means you're transmitting in 360 degrees in all directions, really, around the antenna. Now, why do we want to use horizontal antennas? Well, horizontal antennas are used primarily in HF communications. Why is that? Because you have lower frequencies, which means you have bigger antennas, and it's a lot easier to construct and build these antennas when you lay them out horizontally. Example, a wire antenna can be hung up between two fixed points and laid out horizontally across your yard. Figure one end is attached to a house or one end is attached to a tree, and then you attach one end to a mast, or the halfway point goes to a mast and you have an inverted V, or you have a directional antenna that's on a tower with a boom and a rotor, right? Again, fixed in the middle. Horizontally polarized antennas are commonplace on the amateur radio HF spectrum. Now, I have a vertically polarized HF antenna in my yard because I have a small piece of property and I don't have the room not only to mount a tower, but also to have a large 3-element directional antenna in the middle of my yard. I'd pretty much be hanging over my neighbor's yards. So not that small, but you get the picture here. So why do I have a vertical antenna if most people use horizontal antennas on HF communications? Well, when you talk about going long distance, you're going to be bouncing the RF signal through the ionosphere anyway. And a lot of people, in the theory is that the polarization changes at that point anyway. So it doesn't really matter if you're using horizontal or vertical, but still with the horizontal antennas, typically you get some direction off that as well. So again, if you have your horizontal antenna lane north to south, you'll have directivity east to west. If you have your antenna lane east to west, you'll have directivity north to south. This is why, too, for many people who do shortwave listening, they'll configure their long wire, the random wire antenna into an L-shaped, so they have a north-south and an east-west leg of their antenna. So what about cross-pole antennas? See, this is the cool thing here now. Imagine you've got two vertical antennas, and now you lay them down 45 degrees, and you cross them in the middle. Okay. Again, we talked about the fact that this is good because you get kind of the horizontal and the vertically polarized antenna out of this cross-pole design. Your cell phone is a good example as to exactly why you need a cross-pole antenna. Your cell phone can be laying down on your desk. It can be in your pockets vertically. It could be on your cup holder. It could be in your car. It could be in your gym bag. You're holding it in your hand. Your cell phone is constantly changing its orientation. It's constantly changing from being vertically to horizontal, right, to being side to side or whatever else. Don't forget to, inside of your cell phone, you've got multiple antennas etched into the motherboards, right? You've got antennas in the sides, and in the back, and the front, wherever the antenna may be, right? Because we don't have antennas outside of our cell phones anymore. So you have to figure out that they're squeezing these antennas in somewhere. So maybe they have an antenna that goes up and down, and one that goes left and right. So the antenna is not in a constant plane when it comes to your cell phone. So this is really a great example as to where cross poles are in your day-to-day life, and really you don't even notice it. So that's something to think about as well. Okay, the final one here, and this is a quick episode. Circular polarized examples. Now again, we said satellite communications are great for circular polarized. Now, circular polarized overcomes the spin of satellites, which is what we said earlier. And it also does a really good job of eliminating or ignoring reflections and multi-path distortions. Kind of makes you wonder when you say multi-path distortion, if circularly polarized would be a great way of getting rid of simulcast issues. But I think that's a theory well beyond my pay grade here. It's just something really interesting. But anyway, circular polarized is best used for antennas. And again, you can have the opposite polarization working side by side. So again, you have a right-hand polarization and a left-hand polarization, and because they kind of negate each other and they're kind of immune to one another's signal, you could actually have two signals on the same frequency with opposite polarization, which again, if you think about it, is really cool. So if you're building an antenna for weather satellite operation or ISS or anything else, circular polarized would be really cool to do. And an example of a circular polarized antenna would be something like a helix or even an egg beater antenna. Again, that would be operational for low Earth orbiting satellite reception. Another great example of circular polarized, right-hand circular polarized antennas would be a GPS. Again, I said you use it every single day, and who doesn't use a GPS? And I'm also reading, though, as I was doing research on this podcast, that even some drones might also use circular polarized. So I guess because they're flying and they're coming in at different angles, that they would use that as well. So I want to know, are you using circular polarized on your drones for all your drone flyers? Let me know at scannerschool.com/session 126. So how did we do today? Did we nail polarization or did we lay flat on it? Do you have any ideas or suggestions about how you would help somebody else understand what polarization is? Let us know by going to scannerschool.com/session 126 and leaving a comment on the session notes for this podcast. Remember, you can also join us every Tuesday on Zello. Go to scannerschool.com/Zello. That's like hello, but with a Z or a Z, depending where you live. Scanner School's copyright 2020 Montauk Island Inc. My name is Phil Lichtenberger, and again, this is Scanner School. We teach you everything you need to know about the scanner radio hobby. Next week, we'll talk about Yagi antennas. And this is why we talked about polarization this week, to kind of get you going in the right direction. I know, bad play on words. 73 everyone. We'll talk to you all again next week.